Thanks, Kristen. Kia ora koutou, ko Swan tuku ingoa. I'm one of the co-founders of Growing Point, and we are all about growing soil, food, and community. And we're also a certified soil food web laboratory, which is why I've got my trusty microscope next to me. So we are qualified to be able to do soil food web reports, and that is about quantifying the different groups of microbes in compost and soil. And so tonight I was just going to give you a little sort of snapshot, a tasting platter of microbes, just to do an overview. We are also really passionate about sharing this information and knowledge, and we really saw there was a gap in the composting network in Aotearoa, in that there was a lot of us kind of beavering away, making a lot of compost, but we weren't really quantifying it in terms of the quality and the microbes, which is why we went through these courses and gained that expertise so that we can test it, but we can also share how to make what we call biocomplete compost, because it's super easy and they're inputs that most people have. And I know some of you from the network have already done our Journey to the Centre of Your Compost course, but we would love to see all of you do it. And the next one's coming up in November. So a little plug, shameless plug for that. So I'll just start sharing my screen. Just take you through the basics of what the role of the different microbes are. So what we're looking at is to have a balanced system, and for that we're looking at the four key microbial groups that makes up the soil food web. So that's the fungi, the bacteria, the protozoa, and the nematodes. Now this is the system that's dependent on having living roots in it to be able to cycle all these nutrients and to have the whole growing system in balance. So that's what we're looking for when we take a sample of compost or soil. So just to hold up, this is a little sample I've taken this afternoon from a pile that we made with our last cohort that went through the microscopy course. So it's always fascinating to have a look at what's in there. We can pretty well predict now with our methodology and inputs that we're going to get a biocomplete compost at the end of it. But what's fascinating to us too is with people doing the courses that no matter what your system is and inputs are, if we have a look at them, there's lots of different ways that we can get that biocomplete compost. So we've had a look at food systems, we've had a look at worm farms, food, continuous ad systems, static piles, Johnson Sioux. We've kind of got a pretty broad range of what different types of composts look like under the microscope. So this slide is showing a really beautiful network of fungi through here. These long dark strands are the fungal hyphae. So the fungi is definitely one of the microbes that we pay a lot of attention to. And the longer the strands, an indicator that that's quite a mature pile, that it's possibly been made with quite carbon heavy inputs, because that's the fungi feeds off those more complex inputs. But the other cool thing that starts to happen when the fungal hyphae get longer is that they start to clump together these micro and macro aggregates. So this is actually what's creating our soil structure. And that's an amazing part to actually see with our eyes, the way that the microbes are doing that work. We often misguidedly think that soil structure is kind of a mechanical thing, but the microbes are really play a huge part in creating that structure, creating those clumps that then allow for air passages and water to be able to penetrate into your soil systems and growing systems. So that's what a good proportion of fungi looks like. Then another group is the protozoa. So we've got a beautiful example here of a protozoa, which is a type of testate amoeba. And they're large and golden, and they look like sort of sugary donuts. And I get very excited when I see these. They're beautiful. So that's in the protozoa group. We've got a range of different types of protozoa. The ones that we find most often are the testate amoeba in our particular system. But you can, we also do find flagellates and occasionally ciliates, but the amoeba are the most common of the protozoa group. Another strand of fungi, a different color here, but you can see again these clumps forming around the fungal hyphae, which is what's starting to build that system of soil structure. And it does really highlight the importance of no till, no dig, because it's these fungal hyphae that get broken up when we do that, and that's what starts to denigrate our soil. So, you know, the practice that we employ in the growing methodology is not disturbing the soil as absolutely minimum as possible. And these are the fun guys of the, not fungi, but fun guys of the soil food web. These are our nematodes, and they're very exciting to find in a sample. This one in particular is a bacterial feeding nematode, and they are really important in terms of that poop loop and cycling our nutrients. So you can't see them with your eye. This is at 400 times total magnification. So there's no way you can see this in action, but it's basically a very tiny worm, and the worms are doing a similar function in your system. So at the garden and in the courses that we run, we teach how to make a biocomplete compost pile. This is a methodology that we've learned through Dr. Elaine Ingham's Soil Food Web courses. And it's very simple to do. We use, it's basically 50% carbon, 50% nitrogen. And of that nitrogen, 20% of that is what we call high nitrogen. So it's that party food for the microbes, the party food for the bacteria. And you can use animal manure for that, but we just use freshly cut grass, and that really spikes the temperature in our pile. And that temperature is caused by those bacteria dividing. And so we know that our microbes are kick-started with that temperature spike. It's a single build process, and we just turn it 3 times so that every part of the pile has been what we call hot enough, long enough, so that we know that the whole pile has reached the minimum temperatures. You can also build it, that Tim's created a prototype for us from the carbon cycle bins, and so we've used the open-sided mesh in the carbon cycle bins to do the same methodology, which works really well. And we've also done it with sacks and pallet bays, so you don't have to have exact infrastructure to do it. You can pretty much create something yourself out of very reasonable materials. You can also do it on a large scale with doing the same system in windrows. So here's an example of presenting some live microscopy sessions that we do at the garden, so people can bring along their own samples and we have a look at what microbes are present and give them a bit of feedback in terms of where their system's at. Does it have all those groups? Is one thing dominating another? And it's just an opportunity for people to get hands-on experience looking at their own samples. Another shot of that in the garden. So I thought I'd do just sort of a very quick overview. I was lucky enough to get down to see bEartha in action, and a lot of you will know about bEartha. If you don't know, check out the film, it's amazing. And Ben gave me a guided tour of the system. So it's an in-vessel composter. I was really intrigued to see with such a sped up process what the biology was going to look like in that system. So I flew home with a couple of baggies of compost from bEartha, and one of them was the pile you can see behind me here, which had just come out of the, it was a week old, so it was very, very fresh. It had been processed in vessel. It had reached the temperatures and moisture levels that they needed, and then it had been sitting there. So I was astonished how little recognizable food was in that pile after a week. Really, it was still quite woody because I think he does 50% wood mulch. But it was really well broken down in terms of the nitrogen component, the food scraps there. So I flew back home and I did an analysis of the fresh compost. So I've got a few slides of the fresh compost. I then took another sample of one that had been maturing for 3 months, just to see how the succession of the biology and the balance between the different microbial groups changed in that time frame. So I have to say I was skeptical. I thought, oh, okay, well, an in-vessel system sitting there for 2 weeks, there's not going to really be much evidence of anything other than bacteria. It was definitely bacterial dominant. You can see in this slide all the tiny little dots here, that's bacteria. There was also quite a lot of actinobacteria, which is this tiny little pencil line through here. We could see it with our eye because there was so much of it, which is an indicator that a pile is becoming anaerobic. It's about to turn anaerobic. There's not enough oxygen. So often when particularly the center of a pile has gone really hot, too hot, and it's sucked all the oxygen out, you'll get this sort of layer of ashy, sort of white, dusty. It's often on your woody material. People often think that is fungi, but it's in that circumstance, it's actinobacteria. So I wasn't surprised to see quite a lot of that in this sample. We did see quite a lot of fungal spores. So that round brown dot there is a fungal spore, which is an indicator that the pile will mature and the hyphae will start to grow. So there was, it was expected that there would be a lot of bacteria. It was good to see there were fungal spores so that it can mature into a fungal, a more fungally dominant pile. But there was some evidence of some short fungal strands. So there's a nice fat piece of beneficial fungi through there. We know it's beneficial because it's dark brown and it's got these septor walls. So it's not overly long, but it is nice and fat and dark and brown. So there was a bit of fungi in the fresh pile, and you can see more actinobacteria through here and here. There was also nematodes. So in the fresh pile, I thought, oh, we're not going to find all our 4 groups, but I did. And so this is a lovely bacteria eating nematode, and there were from I think there were in 1 drop of a sample, from memory, I think there are about 7 nematodes in 1 drop, which is good. You know, that's meeting the minimum measures of your nematodes in a biocomplete system. There was also a bit of testate amoeba. So this Arcella testate amoeba was there. And I think there were a couple of flagellates. So yeah, it was surprising that it was that full of all the 4 groups at such an early stage of its development. So I was keen to contrast that with a pile that's been maturing over 3 months. And what you can see here is those fungal spores and those small short sections of hyphae, fungal hyphae, have grown into really substantial long strands of hyphae. So this is at 100 magnification. So if you looked at that with 400 magnification, that's going to be a lovely fat dark brown strand of beneficial fungi. So we could definitely see the progression of that microbial life from fungal spores, short bits of fungi, bacterially dominant, like a lot of bacteria. The bacteria had dropped. What happens when a pile starts maturing? The fungal hyphae grows, gets longer, gets thicker and fatter. It's storing more carbon in those fungal walls. But if you've got presence of protozoa and bacterial eating nematodes, that's going to drop your population of your bacteria. So it's going to start to swing back into balance a bit more, that the fungal to bacteria ratio is going to shift to have less bacteria and more fungi as a pile matures. That's what you're after. And you can see a lovely evidence again of that, the macro aggregates being formed around the fungal hyphae. So it's starting to create that structure in the compost, which is for the air and the water to be able to keep the pile aerobic and a good amount of moisture. You're not moving into a compacted or a waterlogged pile, because that then starts to change the biology into microbes that are going to thrive in an anaerobic environment, a absence of oxygen. We've got some lovely fat strands through here. You can see the branches off those hyphal strands, and the bacteria isn't as dense. There's still a lot of bacteria there, but it's definitely dropped from the example of the fresh pile. So yeah, all that is great. And, the more that we can test out different types of composting methodologies and inputs, the more we gain that knowledge and expertise about how we can bring those microbial groups into balance. But really, it's all about our growing systems, and it's about sinking carbon into our soil. So the compost itself is a vehicle to be able to do that, but we have to apply it. We have to be having a living root in it to lock up that carbon in the soil and suck that carbon dioxide out of the atmosphere, locking it up in the soil. And I know some of you who are present here have got a lot of experience and interest in the carbon sinking qualities of soil, and this biocomplete compost is one way of enhancing that, speeding up that process, so that the carbon and the compost in relation to a growing plant is going to be balancing that system of microbes and locking up our carbon in the soil, in our fungal hyphae walls, and mitigating climate change. Like, why wouldn't we want to do that? So yeah, that's the end of the slides, and I'll stop sharing.